Okay, these are some of the different foods that we test for toxic elements. We test a lot of spices. Spices such as curry powder, turmeric, chili powder, cloves, coriander, oregano, sumac, cumin, ginger, paprika, galangal, pyramid powder, cinnamon, kebab masala powder, to name a few. We also test a lot of candies, such as lollipops, gums, gummies, dried fruit, and many of the candies are from Mexico because we find a lot of lead in those candies. We also test fish that are have high concentrations of mercury, such as swordfish, shark, and tuna. We also test many different types of juices like blueberry juice, cranberry juice. We also test baby foods, and we also got a sample in dirt, and it's edible dirt. We analyzed it, and we got a high level of lead from that one sample. And we also analyzed rice for inorganic arsenic. Next slide. And these are the toxic elements that we analyze for. Lead, inorganic arsenic, which is arsenic 3 and arsenic 5. The 3 and the 5 refer to the number of valence electrons. Mercury, hexavalent chromium, and cadmium. I will talk about the toxic effects of each element, the sources, and major causes of poisoning. Then I'll discuss how we analyze toxic elements in different types of foods and how our instruments work. Next slide. Lead. Toxic effects. Interferes with the development of the nervous system of children. Exposure to lead in early childhood can result in lower IQs, which will eventually cause economic hardships. Can lead to hypertension in adults, and high concentrations can also damage the kidneys. Next slide. Sources of lead. Food stored in lead soldered cans. Certain acidic food can leach the lead out of the can. Crops grown in contaminated soil or irrigated with contaminated water. The contamination from the soil can come from leaded gasoline that was used in the past or leaded paint chips. The contamination in the water can be from older leaded lined pipes. Foods processed with contaminated water. Foods adulterated with lead-containing dyes, such as lead oxide and lead chromate. And the presence of lead shot in meat. I think the lead in shot is banned, but people still have the shot. So one time I actually analyzed some goose meat that was going to be donated to a food pantry, and I found lead pellets in one piece of meat. So I don't think it got delivered to the pantry. Next slide. Lead is one of the only elements that has a limit in food. The FDA has an official limit of 0.1 part per million in candy, but no official limit for lead in spices. So recently, we set a limit of 1 ppm in spices. And currently, we are working with the Department of Health on lowering this limit. Here are some pictures of spices containing excessively high concentrations of lead that I analyzed. We found the spices that contain the highest levels of lead are turmeric, curry, cumin, ginger, cinnamon, and paprika. Recently, there has been many recalls of spices due to high levels of lead. In 2011, Archer Farms and Spice Hunter recalled ground turmeric products for high levels of lead. In 2013, Pran ground turmeric was recalled. Samples collected had concentrations of 28 to 53 parts per million. And in 2016, 7 brands of ground turmeric distributed by the Gel Spice Corporation was recalled. And 38,000 pounds of turmeric from Spice USA was also recalled. Next slide. And here's a first example of lead poisoning. It occurred in Hungary in 1994. and it was Paprika contaminated with lead oxide. As you can see, Paprika looks very similar to lead oxide. Next slide. And here's a new news article telling about the contamination from the Los Angeles Times. Investigators believe the perpetrators tried to save time and money by artificially drying ripe peppers instead of allowing them to naturally desiccate, which can take up to a year. Peppers dry too quickly and produce a less brilliant red color when ground in spice, food experts say, which likely prompted the tamperers to add the paint agent to improve the looks of their products. So they didn't want to wait for the spices to dry, so they added the lead chromate to make it look like they were ready to sell. Next slide. Here's another case back in 1886 by the Wisconsin State Board of Health found candy contaminated with lead chromate. Next slide. And here's another case of soldiers in Hong Kong being poisoned by lead. In this case, it was curry powder contaminated with lead chromate. They found the chili powder they analyzed had a very high level of 10,800 parts per million, which is incredibly high. Next slide. Now we'll talk about inorganic arsenic, which is arsenic 3 and arsenic 5. Toxic effects, highly carcinogenic. Chronic exposure can damage the central nervous and cardiovascular systems, and also causes skin lesions and pigment changes if high concentrations come into contact with your skin. Next slide. Sources: pesticides and herbicides. Most of those pesticides and herbicides are banned, but it still doesn't prevent people from using the ones they already purchased. And right now, I believe the only pesticide that contains arsenic is used on wood to prevent decay. Crops grown in contaminated soil or irrigated with contaminated water. The soil can be contaminated from pesticides, industrial waste, or mining activities. And the water can be contaminated from certain naturally occurring rock formations, or once again from industrial waste. And foods processed with the contaminated water can accumulate a lot of arsenic too. Next slide. Here's the first example. This is actually one of the worst examples of arsenic poisoning ever. It's arsenic poisoning in Bangladesh. Due to the contamination of surface water with bacteria, tube wells were drilled into the drinking water. They never tested the drinking water for any toxic elements, and unfortunately, high levels of inorganic arsenic were found to occur naturally in the groundwater. After they found people were developing sores on their hands from washing with the water. And another interesting bit of information, in 2016, the World Health Organization estimated that 125 million people in Bangladesh, between 35 to 77 million are at risk of drinking contaminated water with arsenic. Next slide. Arsenic poisoning in infant milk. In Japan in 1955, over 100 infants died from drinking milk contaminated with arsenic. They found that the arsenic came from industrial-grade monosodium phosphate that was added to the milk as a stabilizer. I'm not sure, but I believe the industrial grade was probably cheaper than the cleaner grade that they were supposed to use. So, and next slide. Next toxin is methylmercury. Methylmercury is formed by the action of microbes on inorganic mercury. This transformation occurs in lakes, rivers, wetlands, sediments, soils, and oceans. The inorganic mercury comes from the burning of fossil fuels and from natural sources such as volcanoes, forest fires, and the weathering of certain rocks. The methylmercury will biomagnify up the food chain with the highest concentration in the largest predators. And methylmercury is very poisonous. It's a neurotoxin, and it's highly toxic to the developing brain. Acute exposure symptoms are tingling sensation in fingers and toes, weakness, and hearing and vision loss. Next slide. The sources. Industrial waste. Some companies make methylmercury as a byproduct of the chemicals that they're making, and this byproduct can be emptied into the ocean. Shellfish, where it accumulates in shellfish, and large fish, such as, once again, shark, swordfish, and tuna. Next slide. Menya disease in Japan. The symptoms of this disease range from ataxia, loss of vision, muscle weakness, to paralysis, insanity, and coma. Methylmercury was released from a chemical factory into the ocean. And the methylmercury bioaccumulated in the fish and shellfish that are eaten by locals. As you can see by the pictures, the devastating effects from the methylmercury had on the people in Japan. It is estimated that around 2,265 people had the disease, and 1,784 died from the disease. Next slide. Next toxin is hexavalent chromium. Source. The industrial waste, which was in the Aaron Brockovich movie. The industrial waste came from the Pacific Gas and Electric Company, who dumped the waste into unlined wastewater spreading ponds near the town of Hinckley, California. The wastewater then leached into the groundwater and affected all the people that were drinking the water from the town. And lead chromate added to enhance the color of turmeric. Lead chromate was used as a pigment in paint, and until 1978, paint containing lead chromate was used on school buses. And once again, you can see how the color of lead chromate is very similar to turmeric. It's really hard to tell the difference between the two. Next slide. Toxic effects. Carcinogen and can damage DNA, corrosive and causes nasal damage when breathed in, and a skin irritant. Hexavalent chromium is also used in the tanning industry, and many times people come in contact with high levels of hexavalent chromium while tanning products, and as you can see by the pictures, the devastating effect it has on your skin. And next slide. Next is cadmium. Toxic effects. Damage the body's cardiovascular, gastrointestinal, neurological, reproductive, and respiratory systems. It's cancerous and weakens the bones. Next slide. Sources. Crops grown in contaminated soil and irrigated with contaminated water. The contamination in the soil comes from the overuse of certain fertilizers, from industrial waste, and the weathering of certain types of bedrock. And water contamination comes mostly from industrial waste. Tobacco leaves and rice are two crops that absorb a lot of cadmium from the soil. And also foods processed with contaminated water can absorb a lot of cadmium. Next slide. A-T disease. Cadmium poisoning occurred around 1912 in Toyama Prefecture, Japan. Cadmium was released into the Jinsu River from mining operations. The rice grown in the river absorbed the cadmium. The locals consumed the rice and became severely ill. The symptoms were weak and brittle bones, anemia, and kidney failure. Next slide. And this illustrates the A-T disease. As you can see, the bones are weakened because the cadmium will actually replace the calcium in your bone. And over time, it causes your bones to become flexible as seen by the poor person in the middle of the slide who's bent over. And the other side shows you how other side of the slide shows you how it accumulates in the food, and the people ate the food and got sick. Next slide. Now I'll show you about the actual analysis of the samples for toxic elements. First, all samples are screened with a XRF instrument. XRF stands for X-ray fluorescence. I'm pretty sure some food inspectors are actually using them to look for samples that have high levels of lead, arsenic, cadmium, or mercury. It's very simple to use. It's fast, portable, and non-destructive. It can be used on samples in clear plastic containers, but it can't be used on samples in glass containers because most of the glass has lead inside of it, and it'd give you a false positive for lead. How it works. Basically, X-rays are emitted from the instrument that causes the ejection of an electron. The outer electron will drop down to fill the vacancy, and it emits light. The amount of light emitted is unique for each element. And that's how the XRF system works. It's nice to be able to screen the samples. That way, if there's a sample that's really high, we know we have to dilute it more, so that way we don't contaminate the instruments. And the next slide. Now I'll talk about the sample preparation for total element analysis by ICP-MS, inductively coupled plasma mass spectrometry. Samples are prepared by grinding them into a fine powder or paste. Most samples are cryoground. The samples are then dissolved into hot nitric acid and hydrogen peroxide. A high-powered microwave is used to heat the nitric acid and hydrogen peroxide. And here's a picture of my coworker, William, weighing out some spice into a microwave vessel. And next slide. Here's a picture of the cryo grinder that we use. The samples are frozen with liquid nitrogen and then pounded by a steel impactor. The end result is a fine powder. This is very useful when we're having to grind sticky candy or having to deal with whole spices like whole turmeric roots or whole chilies. Next slide. And these are our two microwave systems, both Mars Express. The sample nitric acid and hydrogen peroxide are combined in a pressurized container. The temperature of the acid is raised above its boiling point, which accelerates the digestion of the sample. If the pressure is too high, the vessel will vent out acid fumes, leaving the elements of interest in the liquid acid in the vessel. So you don't lose any of the elements of interest while the vessel is venting. Next slide. Here's a picture of our acid purification system. Trace metal grade nitric acid is boiled to a still to remove contamination. There's basically 3 grades of nitric acid. Each grade is a little cleaner. There's reagent grade, trace metal grade, and optimal grade. By putting the trace metal grade nitric acid through the still, we're able to clean the acid and get an acid that's similar in grade to the optimal grade. And it is much cheaper to clean our own acid than to buy the cleaner optimal grade nitric acid. So this piece of equipment will save us a lot of money. Next slide. And after the samples are digested in a microwave, they are transferred into plastic volumetric flasks. We use plastic volumetric flasks because, like I said before, glass contains lead in it. And if we put the acid in the glass, it'll leach out the lead from the glass and contaminate our sample. The samples are then centrifuged to remove any inorganic matter and then diluted to fit within the standard curve for quantitation. The volumetric flasks are made of perfluoroalkyl copolymer plastic, and the centrifuge tubes are made of polypropylene plastic. Both plastics are very clean. And all flasks and tubes are acid washed before use. Next slide. And here's a picture of one of our instruments. Inductively coupled plasma mass spectrometry with an ion chromatographic system. This is the single quadrupole instrument. This instrument has an IC system attached for the speciation of arsenic or chromium. I'll discuss the speciation later. And in the middle is the auto sampler where we put the samples. And next slide. And here's a picture of our newer instrument. It is a triple quadrupole ICP-MS. The difference from the triple quadrupole is that it's able to remove interferences that the single quadrupole cannot. And here's a picture of the actual plasma that creates the ions that we analyze. Next slide. And here's an outline of the entire single quadrupole ICP-MS system. I'll go through this outline briefly, and then I'll talk more about each part of the system on later slides. The sample solution, which is from the microwave digestion, is pumped through a nebulizer into a spray chamber. Through the spray chamber, only droplets of the smallest size are allowed into the torch, because large droplets will put out the torch, will put out the plasma. And then when the sample reaches the plasma, positively charged ions are created. These ions then travel through a reaction cell, which is filled with helium. Through the reaction cell, certain interferences are removed. And then your ion of interest goes through the quadrupole mass filter, which allows only ions of certain mass to charge ratio to pass. Now I'll describe each part of the system in a little more detail. Next slide. Sample introduction consists of a nebulizer, the spray chamber, the torch, and the plasma. The sample goes through the nebulizer tip and is sprayed into a spray chamber. In the spray chamber, large droplets are removed, and only smaller droplets are allowed to pass into the plasma. The plasma consists of highly energetic argon ions. It produces a temperature of nearly 5,000 degrees Celsius. Inside the plasma, the elements of interest will lose an electron and cause it to be positively charged. And then these ions will pass into the quadrupole. And there's also a picture of how the droplets, as they travel through the torch, will shrink in size due to the heat and eventually become an ion cloud. Next slide. And this is a cross-section of the quadrupole mass filter, which I described before. It's kind of complicated, but I'll try to explain. The green circle in the middle is basically your ion of interest, be it arsenic, lead, cadmium, or mercury. The ion travels through 4 rods. These rods each have electric fields applied to them, so that only mass to charge ratios of a certain amount will pass through. Each rod has 2 voltages applied. One is a fixed direct current, and the other is an alternating current that cycles with a superimposed radio frequency. The magnitude of the applied electric fields can be manipulated so that only ions with a specific mass to charge ratio can pass. Next slide. Now, these are some of the interferences I was talking before. This table shows interference from molecular ions. These are molecular ions that have the same mass to charge ratio as the element that you're analyzing for. And the next slide will show you how we get rid of these molecular ions. The molecular ions are eliminated through a process called kinetic energy discrimination, KED. Your ions travel through a collision reaction cell, which is basically a quadrupole which allows all ions of any mass to charge ratio to pass. In this cell, there's helium gas, and the molecular ions take up more physical space, so they collide with the helium more readily. And once they collide with the helium, they're rejected by a potential barrier, which makes sure that none of the molecular ions will pass into the quadrupole. And as you see on the left side, the elemental ion is smaller, and there is some collisions that occur, but there are much less collisions that occur. So more of the element that you're looking for will pass into the analyzer quadrupole than the molecular ion, because the molecular ion takes up more space and will collide more. Next slide. And here's an example of how it works for an element that we actually analyze for, 75 arsenic. Once again, I said the helium is added to the reaction cell, and inside the plasma, argon chloride is formed, which has the same mass to charge ratio as the arsenic. So this molecular ion is eliminated by passing through the reaction cell. Since the argon chloride is larger than the arsenic, it will collide more. After the collision, the argon chloride is rejected by the potential barrier at the cell exit. So without this way of removing the interference, we would not be able to analyze for arsenic using ICP. Next slide. Now this is the newer instrument. This allows us to remove interferences that the KD mode can't. It's an ICP triple quad. Here's an example of an interference. Doubly charged samarium has the same mass to charge ratio as 75 arsenic. But they're also similar in size. So the KD mode does not work on the doubly charged samarium. So the triple quad has an additional cell filled with oxygen, where the arsenic will actually combine with the oxygen to form a new molecular ion. This molecular ion has a different mass to charge ratio than the samarium. Then the new molecular ion enters a quadrupole, which removes the doubly charged samarium, because they're different, because now there are different mass to charge ratios. So it changes the mass to charge ratio of the 75 arsenic. That's how it removes the interference. Next slide. And here's an illustration of what I was just talking about. How it's a triple quad. I mean, there's 3 quadrupoles. One separates the 75 arsenic from other ions that have the same, that have different mass to charge ratios. And then it enters the reaction cell and forms a new molecular ion, which has a different mass to charge ratio than, say, the doubly charged samarium, and then enters another quadrupole where the ions are separated according to different mass to charge ratios. And it's also used for selenium, but selenium is not that toxic, so I'm not really concerned about selenium. It's more for use for arsenic. Next slide. Now I'll talk about the elemental speciation analysis. Elemental speciation. It's the identification and quantification of different chemical forms of a particular element. The identification is accomplished by retention time differences on an ion chromatogram column. After the chemicals are separated on the ion chromatogram column, they enter the ICP-MS to be detected. Next slide. And now I'll talk a little bit about the different arsenic species. Arsenic species, this basically is another word for different molecules that contain arsenic. The toxic ones, arsenite and arsenate, also called arsenic 3 and arsenic 5. Because arsenic 3 easily converts to arsenic 5, we report the sum of the arsenic 3 and arsenic 5. Then there's dimethyl arsenate and monomethyl arsenate. They occur in rice and are considerably less toxic than arsenic 3 and arsenic 5. And then we have arsinobutane and arsenochlorine, are relatively non-toxic and are found in seafood. So most seafood has a lot of arsenic, but the arsenic is in a form that is not toxic. So you don't have to worry about arsenic poisoning from eating most seafood. Another thing about the arsenic speciation is that you cannot use concentrated acid like we use in microwave digestion. Because if you use concentrated nitric acid, the DMA, the MMA, the arsinobutane, and the arsenochlorine will convert to arsenic 5. So instead, we have to use diluted hydrochloric acid to extract the species. And the hydrochloric acid is only heated to 110 degrees Celsius, compared to 190 degrees Celsius for the microwave digestion. So it's a softer type of extraction compared to the microwave digestion, which is very energetic and destroys the food, the sample. Next slide. And this is a picture of a chromatogram showing the separation of the different arsenic-containing molecules. The mobile phase, which is the liquid that runs through the column, is ammonium phosphate dibasic solution with germanium internal standard, and is adjusted to pH 8.25 of ammonium hydroxide. The stationary phase is a Hamilton PRP X100 anion exchange column. The anion exchange column has a strong affinity for negatively charged molecules, which is how the molecules are separated on the column. Next slide. Now I'll talk about the more difficult type of speciation, the chromium speciation. We use it to analyze lead chromate that's in spices, because the chromium that's in lead chromate is hexavalent chromium. Hexavalent chromium is extremely toxic, and trivalent chromium is an essential mineral. Hexavalent chromium will convert to trivalent in a concentrated acid and in the presence of organic matter. The conversion of hexavalent to trivalent is slowed in the presence of magnesium. So for extracting it, instead of using concentrated acid, we use an alkaline solution with magnesium. And we shake the sample for 5 minutes at room temperature. So we avoid all heat, and instead of using an acid, we use an alkaline solution. Next slide. And here's a picture of the chromatogram for the chromium speciation. As you see, the chrome 6 is easily separated from the chrome 3. The mobile phase is a diluted nitric acid solution with scanadium internal standard added. And the stationary phase is a Dionex ion pack reverse phase ion column. For reverse phase columns, the column has a strong affinity for less polar compounds, which is how the chromium 6 is separated from the chromium 3. And that's all I have. Do you have any questions?
I believe we do have a question for you. Okay, this question is, how do you determine which products are going to be sampled and tested?
I don't do that. That's food
Yeah.
inspection or.
I was going to pipe in on that, but giving you the opportunity.
I just
So-
analyze what they give me.
Yeah, so this question is from Mary from FDA. Mary, we as food inspectors are trained as to what products have been recalled or products that we know typically are high in lead, like the cans that can leach into the product. Years ago, there were lead soldered cans that we know would leach into the product. That's been banned at this point. However, sometimes we do find that. And in addition, we just know, we're trained on, we just know, we're like psychic here, but we are trained on what is inherent to have concentrations of lead or any kinds of metal contamination. So once we decide that and train our folks to do that, then we send it to the lab. So Thomas actually gets that sample and analyzes it for us. And I hope that answers your question, Mary. We're getting a question here from Bruno. Are you aware of any food contamination or outbreaks coming from the lead contaminated water in Flint, Michigan?
No, I haven't got any samples from Michigan.
Okay.
And I suppose there's a chance that if you're using the water is contaminated with lead to fix food, and if it might absorb the lead, so I'm sure it's a possibility.
Mm-hmm. I know even, so I earlier had mentioned in the very beginning of the morning that I've been on this job for 30 years now, and I want to say about 15 years ago, we did a lot of imported food sampling, and we know, like you had mentioned earlier, Thomas, that in Mexico, a lot of the products do come back because of the soil. And then even we would test lollipops and hot peppered lollipops, and even the piece of stick, the cardboard itself would be contaminated as well. I don't know if that was was contaminated due to the product being, and it would be absorbed into the cardboard stick, or could it possibly just be part of the wood and part of that process that it would make the stick? Do you have any idea on that? It was just a curious question.
Well, I know Mexico used leaded gasoline a lot longer than we did. I don't know if they're still using leaded gasoline, but you use leaded gasoline and it burns off, and the lead goes into the soil and it goes everywhere. So
right,
that could be, they might be growing it in soil that's been contaminated from cars.
Mm-hmm. All right, yeah, interesting.
Or soil that's contaminated with lead paint. I don't know, maybe in Mexico you can still use lead paint.
Right. Yeah, I don't know about that. Yeah, but I know we did get a lot of positive samples from Mexico and other parts of the world, actually, right, in the spices. And I was thinking too, I know someone else, I think it was in New York, we had a CASA conference, Central Atlantic States Associations, many years ago now. And someone from New York City did a presentation about tea, how many teas are contaminated with high levels of lead. And if you go in the grocery store now, it used to be like a little section. Now there are a tremendous amount of teas, not knowing where anything comes from. It'd be interesting to see like what kind of consumer confidence is out there with the tea, because I don't really have much confidence in purchasing like all of these different kinds of teas.
Yeah, I've analyzed the tea before.
Oh yeah?
Yeah, and the tea leaves, it's high, but if you take the tea leaves and make tea like you're going to drink, it's much lower. So hot water does not extract out a lot of the lead. So unless you're actually eating the tea leaves, it's really not too much of an issue.
Oh, okay.
Fortunately.
All right, that's good. It does accumulate though, does it not, in your body? Lead contamination?
Yes, yes, it accumulates in the bones, and then it can be released later in your life.
Yeah. Interesting. All right, I think that we've answered, oh, wait, I have one more. Look at that. Bruno, are there concerns about chemical contaminants in maple syrup?
I've analyzed maple syrup, and I haven't found anything in the maple syrup. I think because most people are using the plastic system, where the plastic is in the tree, not the metal.
So Bruno, you can eat pancakes tomorrow morning.
Yeah, maybe some people are still using the metal. I haven't seen it, so.
All right. So it doesn't sound like a big, so obviously you've sampled it, so you don't come up with a lot of
We used to get a lot of maple syrup in, we don't anymore, so.
But was that mostly for like the standard of identity as opposed to chemical?
Yes, that's what one of my
contamination?
coworkers does, based
Right.
on the color, whether it's dark or light.
Right, right. I think, there's Bruno just responding. He wouldn't stop because of a little bit of lead, but it is good to know.
Yeah, it doesn't really affect older people. It's mostly younger people that the lead affects.
So Bruno, I think you're out of that mix now, Bruno. Don't respond to that. I don't want any more responses from you.
This is Betsy. I do
go ahead, Betsy.
drink a lot of tea, and so years ago they said it had it because sometimes they would drive over it with leaded cars to drive out the tea or to dry out the tea leaves, and I always wondered if that was just an urban myth.
No, it sounds true to me.
So the leaded gas fumes would be landing on the tea that they were dragging?
Yeah, that they were using it to
The
dry
soil?
out the tea, supposedly. Again, I thought it was an urban myth, but I thought that was interesting talking about the lead in tea.
That is interesting, for sure. Well, Thomas, I appreciate your time. I think we're actually out of time, so that was perfect.
Thank you.